Assalamu alaikum. Welcome to lecture 4 of natural language processing. So today we will continue with our discussion on text processing. Uh, we left off last week, last Tuesday. That was the third lecture, and this is the fourth lecture. This Tuesday we did not have a lecture on last Thursday. So we'll make up that lecture later on. But we will continue with the numbering according to how much lectures we have already covered. So this is lecture 4. So today we will discuss tokenization again briefly, just to emphasize the importance of tokenization. After that, we'll talk about text normalization, some steps that can be taken during text normalization. We will briefly talk about sentence segmentation as well, maybe a bit about word segmentation. And then after that, we will start with edit distance, which is a way of measuring the similarity between two strings. So I think that is probably what we will be covering today. We might not finish edit distance completely today, but we will be able to start, inshallah. All right. So you also have your first assignment uploaded. So please start working on that assignment. We have already covered most of the stuff that is tested or assessed in that assignment. And of course, since this is the first assignment, you need to get used to the libraries and so on. So start working on it as soon as possible. And I think as we decided last time, we will have a quiz on Thursday, inshallah, next Thursday, towards the end of class. So I hope all of you are doing well. Omicron is spreading quite rapidly. I think, under the influence of Omicron as well last week. So I still have some after effects. So I hope you will bear with me. Any questions before I get started? All right. So let me share my screen. So besides the lecture, I would strongly also recommend that you do a reading of the book. You have just one main textbook, so that's a plus, I would say. So do spend some time reading the book as well. Plus, I have uploaded a Word document with some links to relevant material on the web. So you might want to browse that as well to supplement your reading. But of course, you can always find additional material using just a simple Google search. So a lot of stuff is available on the web. You can always supplement your reading by going through the web. But do read the textbook. That's priority number 1. All right. So in the last lecture, we talked about two concepts. One was tokens. The other was type. So token was basically a linguistic unit of interest in running text, while type was a unique uh, linguistic unit of interest in the corpus. So the set of types we called a vocabulary. So this is a set of types. So in other words, set of types, it's a set, of course, so there is no duplication. So this can also be thought of as the set of features that we have defined to represent our textual content. So, and in general, V is called vocab size, right? And I will also give it a letter, the size of the V is, let's say, M. And N, let's say, is the total number of tokens in text, in running text, in whichever corpus that you're analyzing. So, and we talked about various ways of defining the types, and we called that process in general called tokenization, trying to extract the relevant types from text. And we said that you can consider each word, unique word in the text as a type, or you can consider each character as a type, or you can also consider any number of sequence of characters between a word and a character as a type as well. We call that subword. So you can use any of these techniques to define your types in your analysis. So just for example's sake, let's say we have a set I, M, and let's say Lahore. So of course here M is equal to 3. So there are 3 words in the vocabulary. So you can think of these 3 words. I mean, of course, there could be words, subword. In this case, they are actual words from the English language. You can think of these 3 words as features. And using these features, you can represent your running text. So let me say again, talking about representation, you can represent these words in some expressive way. One very simple way, which is not very expressive, is just to give them unique IDs. So in which case, for example, V would simply be 1, 2, and 3. Some ID, some unique identifier. So 1 is I, M is 2, and Lahore is 3. So whenever you have any text, so let's say I have a text, I can then write it as 1, 2, 3, for example, if I want to differentiate. 1, 2, 3. So this basically means that you have I, then you have M, and then you have Lahore in this sequence. So if you have something else, let's say 1, 1, 3, 2, 2. So this is the sequence where you have I twice, after one after the other. Then you have 3, which is Lahore, and then you have 2 M's. So in this way, you can represent any running text. And of course, in this running text, you have the number of tokens is higher. So number of tokens is, so N is equal to, of course, 5. Of course, in this case, N is equal to 3. And of course, as we know, so M is equal to 3 as well. But having unique IDs, in this case, just numbers 1, 2, 3, are not very expressive. So one doesn't tell me anything about the word that it represents. Similarly, 2 does not tell me anything about the word. And also 1 and 2, I cannot compare. Of course, you cannot simply say that 2 is greater than 1. Of course, this is nominal. These are nominal values, so you cannot compare as such. So we will study later on this course more expressive ways of representing words or representing types. Types could be characters and subwords and words as well, or any other linguistic unit of interest. So the idea of having those expressive ways is to capture more of the meaning as well as the usage of that word in the text. So, for example, you can have a weight, which is a continuous number, defining or representing a particular token in running text. Or you can even also, weight, of course, is scalar weight. And later on, we will see that we can also represent them with a vector of weights. So vector of weights, meaning that each word, for example, the word I, is represented by 300 values, for example. So those 300 values now can capture much more information regarding this word I. as compared to, let's say, if you represent that word I with just one value. And this is, of course, still better than representing the word I by just a discrete label like one. Okay? So what I wanted to emphasize through this discussion is representation in textual processing and analysis is very important, and it would be a key aspect of our discussion throughout this course. Here we'll just introducing the concepts, and we'll be discussing several ways of representing words and how basically types or features and how they can be exploited to solve problems in NLP. So any questions here? So this was actually a refresher of and a reminder of what we did last week. So last week we also talked about subword tokenization, and we briefly talked about BPE. And I would recommend that you read the section of BPE in the textbook, which is chapter 2. And in the assignment, you have assignment on word piece, and there is some description within the assignment on how to compute word piece. So you will learn about word piece as well as part of your assignment. In the book, they only describe the BPE approach, which is very similar, of course, to the word piece as well. The only difference is the way of selecting the next token to add into the vocabulary. All right. Okay, so now let's move on to normalizations, text normalization. So this is also a part of text processing or pre-processing, if you want to call it. And as the word normalization suggests, it basically means that we are trying to uh, reduce the variation in types. Remember, what is a type? Type is a unique token or a unique linguistic unit of interest in our analysis. And it could be a word, for example. Okay? So we want to reduce the variation. And when I say we want to reduce the variation, or in other words, we want to decrease M, which was what? Vocabulary size. So if you decrease M, so what are the implications? Of course, you probably may reduce noise in analysis, enhance, for example, density of analysis. These are actually basic concepts from data mining, actually, or analysis in general. And of course, reduce dimensionality. So any of these things would generally help in analysis later on. Okay? And of course, you will do the normalizations intelligently, as we will see. All normalizations would not be required in all analysis or in all applications. So let's get started. For example, you can do various things. For example, lower casing. So this is, for example, one normalization that you can do. So if your analysis does not require the distinction between uppercase characters and lowercase characters, then you should standardize them or normalize them to one type only, lowercase them. So in that case, for example, the difference in, let's say, if there's a word called Lahore and there's another word called Lahore, if both of these appear in your corpus, they will be considered as different types. But if you normalize them both to Lahore and Lahore, lowercasing them, then both of them would be the same type and the variety of types would be reduced. or the vocabulary size would be reduced. And the logic between normalization is that we want to reduce the variety as long as it does not impact our final analysis. So, of course, lower casing may not be helpful if you're doing a task like sentiment analysis. So, for example, in sentiment analysis, if someone has written, let's say, great in all caps, this might have greater significance as compared to someone who has written just great in lowercase. So if you are doing sentiment analysis, you may consider, of course, generally in practice, we have seen this also doesn't make much of a difference, but depending on your specific application, it might make a difference. So you would like to then keep the all caps grade and the lower caps grade separately so that you can distinguish between a greater emphasis on this adjective than the other one. So this is lower casing. Of course, you can have various steps of removal of unwanted uh, content, for example. So this is another normalization step that you can do. And again, this is dependent on your application. So what can we do? For example, you can do remove punctuations. So in many applications, punctuations would not make any difference, and punctuations may cause your vocabulary to become very large without helping your analysis. So you would like to remove those punctuations. So for example, uh, let's say, again, taking the same example, let's say great. This is one word great. And let's say someone wrote great with exclamation mark and someone wrote great with two exclamation mark. If you do not remove punctuation, all three would be different types, assuming that you have done tokenization using space delimitation. So they will be of different types and they will be considered to be separate. So in many applications, removing punctuation would be helpful, but for sentiment analysis or any such applications where such punctuation might help you, then you might want to keep them. So oftentimes we get data from different sources. For example, if you scrap the web, you might have a lot of other stuff being captured. So you might want to remove, for example, remove tags and let's say code and pictures, for example, and videos, for example, and so on. Anything that you feel is not relevant for your analysis and it might bloat your vocabulary size, you can remove it. So if you scrap the web, for example, if you dump a web page, so you'll have HTML tags there. So those tags, HTML, like whatever, I don't know what's forgotten the syntax. So you probably have something like this HTML, and then maybe at the end HTML. So these tags may not be very helpful, or there might be tons of other such tags. So there might be even code embedded in the page. There might be other stuff. So if that is not of interest, you should be able to remove it, or you should remove it. And again, all of these removal steps, if you remember, we talked about regular expression. So regular expression would be very helpful in finding such strings and removing them. So that's why we studied regex earlier on. So also you can sometimes remove numbers if they are not required, currency, dates, and so on. Again, depending on your application. But sometimes your application is heavily dependent on, for example, dates. In that case, you will retain the dates. Okay? So we were talking about removal. Sometimes we also want to remove low uh, frequency tokens. So for example, so if a token occurs less than 1% in a corpus, remove it. So again, this is a way of reducing the noise in your analysis. So something is occurring very rarely. Maybe, for example, there's a spelling error. Uh, and of course, we are assuming that the corpus that you're analyzing generally has few spelling errors, and spelling errors do not play a role in your analysis. Then you would like to remove such small variations. So for example, someone wanted to write, let's say, occur, but instead of writing occur, he or she wrote is UCR. So this would, it's a typo, of course, but if you, and of course, OCUR might occur very rarely in your corpus, maybe just one occurrence. So such rare occurrences are also removed to reduce the size of your vocabulary and reduce, of course, noise that might be present in your data set. So this criteria, how much percentage you want to, what is considered to be an ideal percentage, actually there is no hard and fast rule there. Uh, so, so usually if your corpus is huge, let's say if your corpus has tens of thousands of tokens, let's say more than 100,000, then usually any token that occurs 10 times or 5 times, which is generally considered to be very small, and those are usually removed or can be removed. Not usually, it depends on the application. They can be removed. Okay. So any questions so far? Okay, so anything else that you might want to remove in some analysis? I've talked about punctuation, dates, numbers, code, HTML. Uh, so just one thing, sometimes, of course, not always, we would like to preserve the sequence of uh, text, but still remove some missing components. So for example, let's say, so you would probably then generate a new text. So I live in Lahore. Okay, let me, I always start with this example. The price was, so let's say you had removed currencies or price items. So you will add a new token, maybe, uh, and call it, let's say, RM bracket, and then continue. Uh, this was uh, on, let's say, discount. So you will replace that removed item with a standard token. Like in this case, I just defined a token bracket RM bracket. So this, what this does is you maintain the sequence of characters and words in your corpus, if that is important in your analysis. So is this point clear? Okay, so regarding normalizations, there are two other common things that are often done, and both of these are done on word level. So one is called stemming, the other is called lemmatization. And usually for any given analysis, we do not do both of them. We only do one of these two. Okay? So this normalization, of course, is done at word level. So some of the previous normalization, you can see that we have done using at character level. So what is stemming? Stemming, actually, the word stem is comes from the study of from the study field which is called morphology. Morphology. So remember we talked about linguistics, I think a couple of lectures back, and we said that morphology is a branch of linguistics. So anyone remembers that? So what is morphology? So morphology studies words and their forms and how uh, these forms change their syntactic, or you can say grammatical usage in sentences. So that is the branch called morphology. So to explain, for example, so for example, so you have you can take any word, let's say. So in general, let me first write you. In general, you can divide the components of words in English, of course, by in this way. At the start, you have what is called a prefix, then you have the stem, and then you have the uh, suffix. So in the very simplest form, any word in English, of course, this is a very simplistic view. We are not going into the depth of morphology. We just want to understand the basic concept. In the very simplistic view, you can have these three components in any word in English. So for example, non uh, dash डाल देता हूँ, non-compliance, for example. So none here is a prefix. Compliance uh, is the stem. So stem basically is the main stem is basically the main meaning bearing component of a word. Okay? So for example, if I have a word called running, so here run is the stem, and then of course you can think of the ing. In this case, actually there are also ning, but let me just, of course, there's a lot of complexity in linguistic. We are not going to those complexities. Running or ning would be the suffix. Okay? And you can have other example, let's say quick. So this is a stem. You can also have quickly. Ly is a suffix, right? And similarly, you can have various other such examples. Of course, stemming would typically only work, or it works on, doesn't work on nouns, for example. So nouns are proper names. So typically, uh, actually, they doesn't work on proper nouns. It does work on nouns as well. For example, you can have things like tables. So this s is a suffix. So table and tables. So what is the idea in stemming? So the idea in stemming again is, as you can see, instead of keeping table and tables with the S at the end as separate types, we would like to normalize them to one type, because essentially there is very little difference in meaning between the two. And for most analysis, we would like to collapse it to type. And what is uh, collapse it to one type? And what is the type that is of interest? The stem, the root bearing, the core meaning bearing component of the word. So stemming is thus the process of converting words to their stems. So stemming, the process of converting words to their stems. So you can, and of course, there are various algorithms available for stemming out there. Uh, most of the algorithms are rule-based, and they apply on the words, you can say, iteratively until they have obtained the necessary stems for each words. So once you have obtained the stems, you now analyze your data at the stem level and you remove the variations. So for example, if you're doing stemming, so tables and table both would be converted to table and table. In other words, there is no variation. It's considered just one type in your vocabulary. So there are a number of stammers out there. The most common one is called the Porter stammer in the English language. So Porter stammer is rule-based. You have tons of implementations of the Porter stammer available out there. You can find it in NLTK as well, the library, Python library for NLP. And of course, there are other stammers as well. For example, there is a stammer called K-stem, and so on. There are others as well. So the stammers would have a set of rules. Those rules would go over all the words in your corpus and try to uh, find the stems for those words. Once those stems have been found, you can then go ahead and work with the stems only for your corpus. So stemming, as I said, is rule-based. So it does have, it can generate errors. So there is nothing like perfect stemming. So you can have, for example, study and studies, for example, might be removed to reduced to stud. But as you know, stud is a separate word in the English language. So there is an overlap. So let's say in your actual corpus, uh, you you do have stud as a correct common word, and also you have the word study. So after stemming, both of them would become stud, and you would be able to distinguish between the two words. So whether it was study or it was stud. So such errors are possible. Another issue with stemming might be, for example, you have uh, automatic. So automatically, and so on, so many variations. This might be stemmed to something like automat. So automat now is not actually a proper word. It's not a word in the English language. So of course, if you want to match, let's say after the analysis, post-analysis of your application, you would like to match a word back to the dictionary, it would be hard to find automat in the dictionary, or you will not find automat in the dictionary. So such issues can also arise in stemming. But stemming, as I said, can be done. And in general, it does improve the performance of many NLP tasks and applications. So the, the benefits that you get by reducing the distinction in types is often much more than the disadvantages that you get as a result of some of these issues or errors that you get in stemming. All right. Any questions? All right. All right. So that was stemming. As I said, instead of stemming, you can also do lemmatization. So lemmatization basically is replacing each word with its lemma. Lemma, of course, is uh, you, you can think of lemma as something that you have used in math, for example, a theorem and a lemma, uh, which can be considered to be the same here, but in more layman terms, lemma is like the root word of a word. So, for example, run, running, ran, runs. The lemma for this would be just run. So lemma essentially is a root word, or you can also think of as lemma uh, as the main word in the dictionary under which all its variants are written. So if you open any dictionary, you will have the word run as the heading, and under it you will also mention its various other forms like running, runs, and so on. So run thus is the root word for all of these variants of this word. So to map variants of a word to its root word is thus called lemmatization. And as you can see, to do lemmatization, you need a dictionary of that language. For many stemming jobs or stemming algorithms, you do not need a dictionary. But for lemmatization, you do need a dictionary. Stemming is typically done with a set of rules, and of course, those rules are language dependent. You cannot apply a stammer for English to, for example, German or for even Urdu, for example. So, so stammer is language specific, and for lemmatization, you need the language dictionary. So all of these variations of run would thus have just one type, and you are thus able to reduce the size of your vocabulary and hopefully also improve the uh, quality of your results of any NLP task down the road. So nowadays, generally, lemmatization is preferred. Although here again, there might be errors, but these errors are generally slightly lesser than stemming. So nowadays, lemmatization is generally preferred because you do not get words that are not in the dictionary at the end of lemmatization. Okay, any questions? All right. So So we have talked about several normalization techniques: lower casing, punctuation removal, date removal, uh, code removal, and stuff like that. And then we talked about stemming or lemmatization. Uh, you can also, of course, remove rare words, rare tokens in your corpus. And of course, you can have other normalizations dependent on your applications that can be done. So, for example, of course, I would not call that strictly normalization, but it's still removal. So, for example, if you want to do simple sentiment analysis, so you can do simple sentiment analysis with just nouns uh, and let's say adjectives. So you do not need the other various uh, part of speech in the text. So you can remove all of that. So for example, uh, uh, so you can have any sentence like the camera uh, was extremely heavy, for example. So in this case, you will just retain the nouns and the adjectives. Of course, extremely is here is an adverb. So you can keep adverbs as well. But let's say if I want to leave it to just nouns and adjective, then I'll just be considering camera and heavy. And for very simple analysis, I might be able to do a good job of sentiment. I do not need the other words. So you can have other ways of processing your text before you do your final application. All right. So one other comment, we talked about morphology. So morphology, as I said, was the study of words and its various forms. So sometimes these forms are also called inflected forms, because this is also a word from linguistic, inflections of a word. Uh, some languages are some so some languages are called morphologically rich, meaning that for each word there might be tons of variations or lots of variations. And the typical example here is Arabic, for example. It's morphologically rich. So one word, one root word may have various variation that might indicate singularity, plurality, uh, past tense, present tense, and so on. So all of these variations can be made to a particular word to represent these various grammatical usages, as well as sometimes even change of meanings. So Arabic is morphologically rich. Even Urdu is also morphologically rich as compared to English. For example, Urdu में even जो verb है वो change हो जाता है according to gender. खाना खा रहा है या रही है. So all of these can change. So Urdu also is morphologically rich. Arabic is of course quite rich. Urdu of course is derived from Persian and Arabic. So it's also uh, morphologically rich. So for such languages, morphology, uh, first of all, is difficult. And secondly, uh, it does creates a larger amount of noise in your analysis. And also, we don't have very accurate ways of normalizing or stemming them. Usually for these languages, we go towards lemmatization, which is usually more accurate than stammer. Okay, so talking about Urdu, Urdu is written in, of course, the Persian/Arabic script, uh, the normal Urdu script. And unless you have typed it in modern day typewriters, not modern day computers actually, you would typically have a space between words, or you will enter a space between words. But in the actual language, you don't have a notion of space as you have a notion of space in the English language. So you will think of the words as just jumbled up, written together, all the characters are written together. So in such language, you would like to separate out the words. Remember, for separating out words in English, we simply did space delimited tokenization. That gives you a fairly good tokenization. But if spaces are not meant for delimiting words in a particular language, let's say in Urdu and of course in Chinese and other languages like Japanese, then you will have to have some other way of finding words. So usually we will find those words using language modeling, and we have not studied language modeling so far. And generally language modeling would give you good results. So, but in the slides and in the chapter, there's a mention of one simple technique, which is of course not very accurate in most cases. But I'll just briefly mention it, which is called the max match word segmentation. So you can think of this as a very simple baseline for segmenting words if the words are not uh, space delimited, or you cannot find the word through any other technique. It's just like a sequence of characters. So, okay. So actually the description here is also very naive. I just wanted to give you the idea. उसमें slide में ये example दी हुई है, वही मैं लिख लेता हूँ. क्या थी वो example? So for example, you have the table down there. So you notice that there's no spaces. By the way, no spaces English में भी आ जाते हैं, often arise in English if you do a scan. So if you scan any document, oftentimes the scanner may make mistake and just have the entire sequence of characters without putting a space between it. So how would you know which word is word? Of course, you can use a dictionary, and in maximum match word segmentation, you also need a dictionary. So in maximum, how does this work? So you start with the start of the sequence. So you have your, let's say, your cursor at T, and you move forward. You go to H. So now you have the complete sequence TH. Keep the mic unmuted. Okay. So we have, you start from T, you move one step ahead. T आपने देखा कि dictionary में है कि नहीं है, so there is no word called T in the dictionary. You move forward by one, you H, TH dictionary में है कि नहीं है, it's not there. So you move forward again. E, so THE dictionary में है, so this is a potential word and this is a potential place at which you can segment. So dictionary होना जरूरी है, ठीक है? But since this is a greedy approach, maximum match, you say, okay, let me try the next as well. So you go to T, ठीक है? So इसके बाद THE, T again dictionary में available नहीं है. फिर आगे गए थीटा. अब देखा थीटा देखा तो ये भी dictionary में available है, right? So, and if you continue in this fashion, you find that the maximum size that you have found is theta. So theta पे आप ब्रेक लगा देते हैं, ठीक है? पूरा आपने एंड तक गए और देखा कि कौन सा सबसे बड़ा वर्ड मिलता है डिक्शनरी में। टी से शुरू किया, HETA, आगे ये भी, आगे सारा एंड तक देखा आपने, राइट? बट द मैक्सिमम वर्ड दैट यू फाउंड दैट वाज इन अ डिक्शनरी वाज थीटा। तो यहाँ आपने ब्रेक लगा दी और यू कंसिडर दिस टू बी ए वर्ड, देन यू मूव योर कर्सर टू द नेक्स्ट एंड रिपीट द स्टेप्स। तो बी पे आपने रखा, कुछ नहीं मिला डिक्शनरी में, BL कुछ नहीं है, ई कुछ नहीं है, डी है, ब्लड डिक्शनरी मिल जाएगा। पूरा आपने देखा, फिर आगे सो OWN, सो ये और कुछ नहीं मिलेगा, सो यू स्टॉप एट ब्लड। सो ये ब्लड आ गया, उसके बाद आप गए and so on. So you notice that in English, you might get wrong results by this very simple algorithm. Of course, if you modify this algorithm using a dictionary and some other intelligence, you might get better results. But the very basic algorithm is what? Start at the start of the string, go to the end, and find the maximum length of the word that occurs in a dictionary. Once you have found it, you move your cursor to that point. Then you start again from that new point and go to the end, find the next longest word. Greedy approach. Then do that and continue in this fashion. So for English, it doesn't work that well, but it has been found that it works well for some languages, especially for Chinese, even though it's a very simple algorithm, but it works very well for Chinese. And for Urdu also, it works reasonably well, not very well, but it works, doesn't work very well for, in general, English. But we have more sophisticated techniques for word segmentation, and most of them are based on language modeling, which is basically probabilistic in nature. So we will consider language modeling later on, and you will get a better idea. But if you want a very simple baseline, then this is one of them, max match word segmentation. So is this algorithm clear? Of course, this is a greedy algorithm, and there was a question somewhere. Okay. All right. All right, so let's move on. So now just finally we'll talk about, before we move on to edit distance, actually we're running out of time, but very quickly, sentence segmentation. So oftentimes we have running text and we would like to separate them into sentences. And of course, this is also language dependent. And again, if you think of a baseline approach, we can use a simple rule-based approach. So a simple rule-based approach may be thought of as like a decision tree. So in the English language, how can you determine that you have come to the end of a sentence? So you can have various things. Let me just go to the slide so that I can move quickly, although it's not a big thing. Slide में एक slide दी हुई है. So you can look at this decision tree, which is again a rule-based approach for determining whether you have reached or you have found the end of a sentence. So you can think of a root. At the root, you check whether after a character there are lots of empty spaces, or let's say empty lines. If that is true, it means that you have reached the end of a sentence. If it is not true, then you check whether the last character is a, for example, a question mark, or let's say a colon, double dot. So if that is the case, then you say it's end of sentence. If not, then you check if the end of the sentence is a period. So if it is a period, then you need to further check whether this period is part of some other uh, uh, sequence of words. For example, if period uh, is part of, for example, a number, for example, or it's part of an acronym, then it may not be an end of sentence. But if it is not, then it's an end of sentence. So in other words, from this simple set of rules, you notice that it's still not always 100% possible to detect the end of a sentence by some set of rules. The period, which we typically assume would be a good indicator of end of sentence, it is actually not, because the period is used as part of numbers also. So 3.1, for example, it can be used as full stops in acronyms like, for example, PhD, PH.D, and so on. So, so period is generally not a good indicator of an end of sentence. So usually in practice, we use again language modeling, and we use some machine learning approach. We define a feature set and train a machine learning approach like logistic regression or even a decision tree to learn the rules automatically. So you need to have a training data set, you need to have a labeled data set, learn a classifier like logistic regression or naive Bayes or decision tree, and then use it for classification. So, for example, if you're designing a decision or a machine learning approach, you will have to define a set of features. So features could be what is at the end of, is it a period, is it a question mark, is it a colon, or it could be other things as well. What happens after a period? For example, that could be a feature. Is it capitalized or is not capitalized? Is there a space after a period or not? So are there numbers around a period or not? So you can have various such features and design a training data set and train a learning algorithm. So you can also use the length of the words as well. So probability of word that comes after a period, probability of word that comes before a period, and so on. So usually when a sentence starts, it usually starts with some limited number of words. So for example, the, I, he, you will not have a new sentence starting with some verb, for example, running. So new sentence typically would not start with running, for example. So you can use all of these clues and build a good machine learning model for sentence segmentation. Okay. One final thing before I move on to edit distance. So we have talked about words, we have talked about subwords and characters, and we said that these were actually features in our analysis. Uh, so, but what is the unit of our analysis? So, so those are features. So generally, when we talked about features, we talk about objects also. What is a data object? So generally, जब हम features की बात करते हैं, let's say we have a student, which is the object. And then for each student, we have features like age, gender, and so on. So now we have features like words, I, am, Lahore, is, living, there, so on. These are features. So what is the object of analysis? So object of analysis could be anything. It could be, for example, a phrase. If you think of a small sequence of words, it could be a sentence. It could be a paragraph. It could be, for example, a section in a document. It can be a complete document. It could be a set of documents, and so on. So our object of analysis would be different, and of course, it will vary according to our application. But in most NLP, whatever our object of document is, we simply call it a document. So for example, one document might be one tweet or one Facebook status update, or it could be a complete research paper, uh, let's say on IEEE Explorer, or it could be one sentence. So depending on what you consider to be your unit of analysis, we call that generally as a doc in most NLP application. Okay? So in other words, at the end of the day, you will have a set of docs to be analyzed, and each doc is defined by a set of uh, the vocabulary set. Okay? So those docs could be, let's say, paragraphs, and vocabulary set, of course, is the V that we talked about earlier. Uh, it is the set of unique tokens of interest in the set of documents. All right. So now let's move on to the edit distance. We won't be able to do much of here. We have 15 minutes left. Okay. So what is edit distance? You might have heard about edit distance many times before, and you might know about it. Uh, but what is the motivation behind edit distance? So when we have two strings, we like to be able to. So one thing is you want to match strings. Match is exact matching. But when there is not an exact matching, you might want to have some continuous way of gauging the similarity between those two strings. So one way of doing that is the edit distance. And edit distance is the fundamental way, and based on this, there are some other ways like the longest common subsequence. And also you can relate edit distance to the Hamming distance also. Hamming distance, you might have heard about the Hamming distance somewhere else as well. So you can relate that to Hamming distance. So we'll talk about this probably next time. So one very simple application of edit distance is to find how similar two strings are. And of course, the application is spell correction. So if user types something like, so basically GRA, trying to write giraffe or graft or whatever. So based on whatever the user had typed, we would like to find the word that is closest to this typed word in the dictionary. Dictionary, of course, has all the words in the correct spelling. So you need a ranking. Ranking is, of course, then based on some, you can say, a metric or a measure, uh, which will give you a number, and then you can, based on that number, you can rank. So this number can be given by this technique called edit distance. Okay? So based on that, you can then recommend the word that has the lowest edit distance with the one that was typed but was not found in the dictionary. So the minimum edit distance actually is the minimum edit distance. Sometimes you will find it written as the minimum edit distance, but whenever you say edit distance, by definition, it is the minimum distance between two strings, and that distance is the minimum number of operations to transform one string to the other string. So those operations are insertion, deletion, and substitutions. And sometimes these number of operations might be different. And because of this operations difference, we call them slightly different measures. So edit distance allow all of these three operations: insertion, deletion, and substitution. So the minimum number of insertions, deletions, and substitutions required to transform one string X to another string Y. These two strings need not be of the same length. And that is one of the advantages of edit distance as compared to Hamming distance. Hamming distance requires that both strings are of the same length. Okay. So let's say you have two words, intention and execution. So usually when you are computing the edit distance, you also implicitly are aligning those two strings. So you're aligning such that whenever you're doing a substitution, there should be replacement of the word. And of course, when there is no substitution, the two words would match. And you will move the strings left and right such that you get uh, the minimum number of operations to transform one to the other. If you count each operation, let's say insertion is cost 1, deletion is cost 1, and substitution is cost 1, you can count all of these cost and call this the minimum edit distance as a number, as a value. Okay? So higher the value, the greater the dissimilarity. The lower the value, of course, if the minimum edit distance is 0, it means that it's exact match. So now the question is, how do you go about finding this minimum radius? And this is where it becomes a bit interesting. Otherwise, this is quite simple. It turns out that it's not trivial to find edit distance between two strings of different lengths. And you need some algorithm to do it. So you're also running out of time. So edit distance, as said, is a way of quantifying the similarity or dissimilarity between two strings. The two strings need not be of the same length. So let's say I have one string cat and the other, let's say, string is, just to make it very simple, BET, bet. Okay? So we said that the minimum number of insertion, deletions, and to move from one string to the other string. So if I'm starting from cat. What can I do? If I remove C, I get 80. If I add B, I get BAT. If I substitute E, I get BET, right? So this is one sequence of operations that you can go to get bet. But it turns out that this sequence of operations is not unique in the sense that You can go to bed in different ways. So cat. So I can even say, let's say, for example, so I can replace C with B. Let's say substitution is allowed. Okay? I get direct bat, and then I get BET. Or I can do other tricks as well. Let's say I remove C, I also remove A, and then I add B, T, and then add ET. So you can go through various operations to get to the end result. Of course, what we want is the minimum number of operations. And when I say minimum number of operations, minimum cost. Let's say there's a cost associated with each operation. I will want to have that set of sequence of operation that would result in the minimum cost. So as you can see, there's a notion of minimality or optimality. So it's kind of solving a search problem, an optimization problem. And usually we'll do this in a systematic way. And the algorithm that we'll use from algorithms is called dynamic programming. And we'll discuss this next time. So it turns out that you can use dynamic programming, which is a structured way of solving, you can say, structured problems uh, efficiently. And in this case, you can solve this edit distance problems using dynamic programming. So we'll discuss this then next time, inshallah. So in the next class, we'll probably be finishing with edit distance and we'll move on to language modeling. And also in the next class, as I said, we will have a quiz at the end of the class. And all my quizzes would include whatever has been covered till the previous lecture. Any questions? Uh, the starting time of the quiz would be around 11:05. So I would strongly suggest that if you are joining just for the quiz, you should join at 11, no later than 11. And we will communicate the details later on, but you will need to have your camera on during the quiz as well. Quiz, of course, would be on LMS text and quizzes.